We are going to continue our discussion about Karnaugh maps, and we're going to do so by kind of solidifying a set of a procedure that we'll go through in order to take our, well, we already know how to convert our truth table into a Karnaugh map, but we're going to solidify our procedure for identifying these pairs, these groups of terms that are going to create, or these groups of ones that are going to create products in our sum of products expression. Let's go ahead and do another one of these conversions from a truth table to the Karnaugh map. And I don't know, let's just make up another truth table. We've got, we're sitting around the conference room table. We've designed this procedure and we've decided that this is the pattern of ones and zeros that have to come out of this circuit that we're going to design, this Boolean expression that we're going to design. Now, remember, the goal was to take this truth table and rearrange the rows so that we set up the ones that are going to simplify into simpler products, we set them up next to each other. Now, what we're going to do is we're going to do our Karnaugh map. We're going to set it up and do it in the fashion that we're going to use for the rest of this topic. What you're going to do is, remember, from last lesson, we labeled the rows with the different values for A and B. So what we're going to do is we're going to just simply put an A and B here to identify that that's what we're using to distinguish each row from each other, or the different values for A and B. So we're going to do A is 0, B is 0. A is 0, B is 1. Now remember, the Karnaugh map works because the neighboring cells, row to row to row, or column to column to column, only differ by one input variable. So we have to use gray code whenever we're numbering these. So we go 0, 0, 0, 1, 1, 1, and then 1, 0. And that gray code, remember, it's cyclic, so we go 0, 0, 0, 1, 1, 1, 1, 0, and then it can loop around so that actually this top row and the bottom row, they're actually adjacent to each other. Now we're going to identify the columns with the different values of C. And so that's really how we're going to lay this out before we map our truth table over to the Karnaugh map. Now, let's do the mapping. So this cell right here is the cell where A is 0, B is 0, C is 0. So that's our top row here. So this 0 right there goes there. All right. This next cell right here, this is for A is 0, B is 0, C is 1, 0, 0, 1. That 1 goes in that cell. All right. Next cell, this cell right here is A is 0, B is 1, C is 0, 0, 1, 0. That 1 goes into that cell. This cell right here is 0, 1, 1, 0, 1, 1. That 1 goes into that cell. And what's cool is that we've already seen that we've got ones next to each other, which means things are going to simplify. Understand that the product we can't simplify is a 1 that is all by itself, that's surrounded entirely by zeros. All right, now, next one, we've got this cell right here. Now, because of the gray code, we're going to take this little hop across a couple of rows in our truth table. This cell right here is actually where A is 1, B is 1, C is 0. 1, 1, 0, there's a 1 there. And we already see we've got another pair happening right there, don't we? All right, this cell right here, that is A is 1, B is 1, C is 1. This bottom row, there's a 0 there. All right. And then this cell right here, we're going to go back and capture those rows we skipped over. So we've got A is 1, B is 0, C is 0, 1, 0, 0. There's a 0 there. And then this cell right here is 1, 0, 1, 1, 0, 1. There's a 1 there. All right. Now, what's interesting about this is that the information that's contained in the truth table is all contained in the Karnaugh map. There's no information lost by moving to the Karnaugh map. So actually, we can get rid of the truth table. And in fact, I just said that there's no information lost in the truth table, but actually there's information gained in the Karnaugh map. So all the information that is in the truth table is in the Karnaugh map, plus a little something extra. Now, let's talk about how to make rectangles. So I'm going to make some rules for making rectangles. All right. Rules for, there's a lot of quotation marks up there, aren't there? Let's get rid of a couple of them, make it look a little bit more professional, right? All right, rules for making rectangles. All right. Now, the reason why I call these rules for making rectangles is because as long as the Karnaugh map does great things for us, as long as we follow some simple rules. Now, the very first rule is, and remember what our goal is. Our goal is to make products. And remember, products generate ones. So I've got a product, we did it whenever we started with the truth table. We picked a row with a 1, we made a product. Did nothing with the zeros. The zeros work out for themselves. But what we're going to be doing is each one of these rectangles that we're going to draw, we're going to group these ones into these rectangles. Each one of these rectangles is going to generate a product. So for every rectangle, there will be a product. Now, remember, products generate ones. So the very first thing we need to do is we need to make sure that there is a rectangle for all of the ones that are in this Karnaugh map. In other words, we can't leave a 1 out or our expression is not going to generate the 1 for that. So the first rule is all ones in the Karnaugh map must be covered by at least, notice I said at least, 1 rectangle. All right, so we are going to basically create these rectangles that are covering up the ones, and by the time, it's a puzzle, and by the time we've finished adding all of our rectangles, every one will be covered by at least 1 rectangle. All right. Now, second thing. Whenever you're creating one of these simplified products, remember the way it worked was, and I'll just do a quick example here. If I had something like A, C bar. Now, the way this works, if we just had 3 inputs, A, B, and C, to this circuit, we would say that this product outputs a 1 as long as A is a 1 and C is a 0. B can be whatever it wants to be. Now, how many ways can B be? Well, B can be 2 different ways, right? So this is actually going to result in 2 1s in our truth table or 2 1s in our Karnaugh map. What if this same product was actually for a circuit that had 4 inputs, A, B, C, D? Well, in that case, we'd say that A has to be a 1, C has to be a 0, but B and D can be whatever they want. How many ways can B and D be whatever they want? Well, 2 times 2, or 4. So it has to be 4 ways, all right? If I had 5 inputs, there'd be 3 variables that could be whatever they wanted to be, and there are 8 ways that would happen. So when we're making a rectangle, we have to cover all of those possibilities with a single rectangle. So if we're going back to just 3 inputs here, and B can be whatever it wants to be, the rectangle has to cover the value for A is 1, B is 0, C is 0, and for A is 1, B is 1, C is 0. So it'll be a size of 2. If we had the D, it will actually be a size of 4. If we had an E, it would be a size of 8. And so the whole idea is that these rectangles have to cover all the possible combinations of 1s and 0s, and hence they must be a power of 2. The number of cells must be a power of 2. So 2, the number of cells covered by a rectangle. Must be a power of 2. And this gives us what? 1 is a power of 2, right? And the funny thing about 1, and then not a funny thing, because what that means is there's 1 cell that has all 0s next to it. and it won't simplify. So that particular cell is going to require all of the inputs. So 1, 2, 4, 8, and so on. All right. So the size of our rectangle must be a power of 2. All right. So next rule for making rectangles. Next rule for making rectangles. What is the next rule? Rectangles may overlap. But, there's always a but, isn't there? As I said, in a Karnaugh map, all ones must be covered by at least one rectangle, but they could be covered by more than one rectangle. So, rectangles may overlap, but every rectangle must have at least one cell unique to it. All right. All right. Now, why must this be true? Well, it turns out that, remember, if we're making rectangles to generate products for our sum of products expression, if I have a rectangle that is fully overlapped by other rectangles are already generating those ones. Other products are already generating those ones. And this rectangle that doesn't have a unique cell is redundant. It's not adding anything to our expression, and it can be removed. All right. Fourth one. Let's see. I think, yeah, I got all ones, blah, 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 blah. Let's see. Well, there's a pretty simple one. No rectangle can contain a 0. That's pretty simple, right? 5. Rectangles may cross from top to bottom and left to right. In other words, they may cross borders. Now, this is all based on that fact that we've got this numbered in gray code. So this cell right here, this one right here, is actually adjacent to this one. Those two are adjacent because of gray code. We can also, we'll see whenever we spread things out to a 4x4 Karnaugh map, that left to right, those are also going to be adjacent to one another. Now, the last one. And what this does for us is it's going to give us the most simplified expression. In fact, this number 6 is really the meat of what makes Karnaugh maps so helpful to getting simplified sum of products expressions. We need to make, while adhering to all of these rules, make your rectangles as large as possible. So it may be that I have 2 rectangles next to each other that both contain 2. Well, I could actually merge them together into a 4 cell rectangle to simplify that product. Because remember, each rectangle is going to generate a product. And how are we going to make the most simplified? Have as few rectangles as possible. And also, every time we double the size, this is really important, every time we double the size of a rectangle, one variable is going to drop out. We saw that with that product, that example that I did before with A and C bar, or A and C bar. By doubling it, by making it so B can be whatever it wants to be, B drops out of the expression. All right? So let's make some rectangles. All right, this expression, or this Karnaugh map right here, has a number of rectangles in it, right? Now, there's one that is, we're going to have to kind of pay attention to this number 3 here, but for the most part, what I have found in my experience is to just simply find a 1 and make the biggest rectangle we can out of it. All right, so let's start with this 1 in the upper right-hand side. I cannot pair it with the 1 to the left. I can pair it with the 1 below it though. So there's a pair right there. I could make this pair right here. All right. Now, You'll also see, if you look at this rule number 5, that I could have crossed also to go and include the one that's above it, right? And so I could have this one with this one and this one, and all three of them grouped together. Is that a valid rectangle? No, it's not, because it violates the second rule which says every single rectangle must contain a power of 2 number of cells. So I couldn't just reach up and grab that one too. That would be a rectangle of 3 cells. That's a violation of rule number 2. All right. Now, once those two are covered, I don't have to look for any other rectangles. I don't have to worry about those two, any other rectangles for those two ones. They're taken care of. Once we've got a product for them, they're taken care of. So let's go to this guy right here. This guy right here, well, I can't pair it with the one above it, but I can pair it with the one to the right, or I could pair it with the one below it. I can't pair all three of them. That would be a triangle, first of all. Second of all, it would be 3 cells. Which one should I pair it with? Well, I should probably pair it with the one that isn't already paired with anybody. All right? And notice that these two right here, they could have been paired, but if I eventually had to make a rectangle around that one, then the rectangle that I would have added to cover those two would have been a duplicate. And we can't have a duplicate. Each rectangle has to have at least one cell that is unique to it. All right. Now I've got a 0, 0. Now there's only 1, 1 left. This one right here can't be paired with the one to the left, can't be paired with the one above it, but remember, it could be paired with the one below it, which would have us wrapping from bottom to top. Now, have we followed all these rules? Number 1, are there any rectangles we can make bigger? No, because the way you look and see if you can make a rectangle bigger is that you unfold them, you double them. They have to double in size. The second rule, first rule, all ones are covered, right? Second rule, all ones are covered by at least one rectangle, and it's a power of 2. Excuse me. All cells are a power of 2, so I've got 2, 2. They're all 2. Rectangles may overlap, but every one has a unique cell. No rectangle can contain a 0. It doesn't. Rectangles may cross from top to bottom. We've got one of them doing that. And every rectangle is as large as possible. All right. So let's figure this out. Now, we're going to go a little bit more formal method in the next video, but what I want to do is just show you real quick the products that have been made. Let's start out with this guy right here. First of all, I want to see what drops out. What drops out is, well, I stay in this column, which is the 0, C is equal to 0 column. So I know that C is going to be a part of that product. Now, as far as the rows, which rows do I cross? Well, I cross the A is 0, B is 1, and the A is 1, B is 1. So A is the one that goes back and forth. So A drops out. B is what we're left with. All right, so we know the product is going to be B ANDed with C. We just don't know which ones are getting inverted yet. Which ones are getting inverted? Well, B has to, as long as B is a 1 and C is a 0, we're going to output a 1. So that becomes B and C bar. Remember, we're going to go through this in a little bit more detail in the next video. All right, how about this guy right here? What does it cross? Well, it stays in the C equals 1 column, so we know that C is going to be part of the product. It goes across 2 rows, so we know that either A or B are going to drop out. We just need to figure out which one. So A or B is dropping out. We've got 0, 0, and 0, 1. Looks like B is the one that changes between a 0 and a 1, so B drops out, so we get an A. Do we need to invert anything? Well, as long as A is a 0, top 2 rows, and C is a 1, we're going to output a 1. That looks like we invert A, and we get A bar. Now, what about the last rectangle? The last rectangle, well, this one also stays in the C column, specifically C equals 1. But which one does it take, A or B? Well, this one has A is 1, B is 0. The top one has A is 0, B is 0. So A is the one that changes. It drops out. We're left with just B. Is B, so do either of them need to have inverters? Yes. B is 0 means it gets a bar. C is 1 means it does not. And we get the final expression is equal to X is equal to B and C bar, ORed with A bar and C, ORed with B bar and C. Now, isn't that a lot easier than simplification? Takes a huge burden off of us. We don't have to do those 3 identities in the distributive law in order to simplify that mess. We can see it graphically how our system is going to simplify, how our expression is going to simplify, as long as we just get used to using a few simple rules.